Hello, everyone. Hope you had a good lunch today. Hi, my name is Adrian Tang. I'm a third-year PhD student from Columbia University. Today, I'm really excited to share with you our work on detecting malware exploits in an unsupervised manner using lower-level hardware features. And this is joint work with my research advisor, Sal and Simha. Now, before I plunge into the details of our work, I want to begin by spending some time motivating and giving an overview of our work. So as we all know, malware is very widespread, and this coupled with the fact that it is constantly evolving makes it a very significant problem. So to detect malware, there are many different features that we can use. So these features can be abstracted based on how far away they are from the underlying hardware. So generally, as we go, the higher a feature goes, the further away it gets from the hardware, and the more directly it describes the action of the attacker, and consequently more degree of control the attacker will have on the attack. So many earlier works audit the higher level features that includes the OS or the application level observables such as function calls, system calls, or the structure of the binary. So these higher level features describe the semantic and syntactic behavior of the malware. Now, in this work, we introduce the use of lower level features to detect malware exploits. So what exactly is lower level features? So the hardware that we use to run the software is composed of many different smaller hardware units. So these smaller hardware units are what we term as microarchitectural components, and they compose of, they could be like instruction caches or data caches or a translation locus-like buffer. So as the software interacts with the hardware units, many microarchitectural events can be tracked. For example, how many data cache misses you have when the software executes, or how many mispredicted return instructions that you actually occur when the software executes. So when we say lower level features, we refer to this microarchitectural features that describes the interaction of the software with the underlying hardware. So because these features are closer to the hardware, we lose semantic information among several other challenges that we face when we are using these features. However, in return, we gain several advantages. In general, the lower the features goes, the closer they get to the underlying hardware, and the smaller the degree of control the attacker has in manipulating the attack code. So they are actually harder to, it's a lot harder to manipulate code to get, like, for example, an intended level of mispredicted returns. So this compares to like maybe high level features where an attacker can change like the system calls or function calls. It's a lot harder for an attacker to change, for example, I want like a specific intended like mispredicted return. And secondly, because they're closer to the hardware, they are more efficient to collect with widely available hardware support. And thirdly, these events can be represented as a little more than a stream of time series data. So this opens up a possibility of an out-of-VM or possibly a VMI-based kind of deployment without the need to bridge semantic gaps, which is a common problem that we see a lot in a lot of VMI works. So now that we get a general understanding of what lower level features are, I just want to go over like some of the key ideas of our technique in one slide. So to profile the underlying microarchitectural behavior of the program, we rely on hardware performance counters widely available on the processors. So these counters are special registers that are designed in the processors to use to track various microarchitectural and architectural events. And these are traditionally used for debugging and performance optimization purposes. So using these counters, we can collect several low-level events concurrently over time, as you can see over here. And as you can see on the top right-hand corner, we see them as time-aligned time series data. So what happens when a malware exploits a program? Now, this malware will execute within the memory space of the host program and becomes part of the program. And the execution of the malware exploits affects the original baseline microarchitectural profile of this program. And this forms the main intuition behind our work. So the central questions that we have for this work is, can we detect this anomaly caused by malware exploits on the attack programs? And can we actually do it at a lower level where there is little semantic information about the program? And the answer is yes. So for the next 20 minutes, I'm going to share with you some of the challenges that we face in using these hardware features and how we tackle these challenges to detect the exploits. So first off, I'll briefly touch on some related work and where our work is positioned among the malware detection works. So here we map the research space of malware detection work using 4 quadrants. On the y-axis, we show the abstraction level of the features. Recall that we talked about this in the earlier part of the slides. On the x-axis, we classify the detection work based on 2 main approaches, namely the signature-based, misuse-based kind, and the anomaly-based works. So simply put, the signature-based works looks for bad behavior. This is something like, this is roughly a blacklisting versus a whitelisting kind of approach. So signature-based works would be something like a blacklisting, where you look for bad behavior of the malware. And anomaly-based work, what they do is that they profile the normal behavior, and they look for malware that deviates from this normal behavior. So there are a lot of previous work that use features above the microarchitectural features. So for those works that look at the microarchitectural ones, last year, Demi and his colleagues present their work on detecting Android malware apps using microarchitectural features. With supervised learning, they learn the models of good and bad applications to detect malware. So in this work, we advance the use of microarchitectural features to detecting malware and the anomaly that were caused by these Windows exploits, infecting commonly used user programs such as Internet Explorer, PDF Reader, and Flash. So the value of this anomaly-based approach is that it can potentially detect ODAs, as long as they exhibit some form of observable perturbations to the original baseline profile. So this is where we position our work in the 4 quadrant. Now I'll go into the details of the system and methodology. This is an overview of the various stages that we have for our methodology. So the first phase is the collection phase. This is where we collect the data, and this phase consists of the infrastructure that we use to collect the measurements, as well as the process of collecting labeled data from the malware execution. So here's a system overview of how we collect the measurements from a host that we want to protect. The host that we want to protect is on the left side, and then we have a separate system that collects all the data, that collates all the data, and that is used for training and detection purposes. So recall that we use the hardware performance counters to collect the measurements, and here we call it HPC, as you recall, on the bottom left-hand corner there. So we develop a kernel driver that configures the HPCs to collect specific events concurrently. And we also record the PID, the process ID, of the various applications together with the measurements to have an approximate per process measurement. So these measurements and the PID will be transferred over via network to a separate system where they will be stored for training and subsequently for online detection. Now, since we are using unsupervised learning for our model, we don't exactly require the measurements for the training of the model, as in the measurements that are attributed to the malware execution for the training. However, we still require the labeled measurements from the malware execution for 2 main purposes. One is to help us, is to guide us in the selection of the features that we want to use in our model. And 2 is to provide the ground truth for us for testing and evaluation purposes. So now let's take a look at a typical malware exploit. Contrary to what most people may feel about drive-by download being a one-click kind of process, in reality, a typical malware actually infects in a couple of different stages. So we distinguish the execution of the malware into 3 general stages, namely the code reuse section, the stage 1 shellcode, and the stage 2 payload. We have more details about this in the paper, so I invite you to take a look at our papers to look at that. So in general, these stages, they have very different characteristics with different purposes in the infection process. For example, for the code reuse shellcode, this is specifically designed to evade DEP And then they redirect the execution to the stage 1 shellcode to do further infection. So generally, there are two main kinds of code we use, but because we only see the raw kind of shellcode in a while, so we would just term this code reuse shellcode as the raw. So we believe that different stages of the malware, because they exhibit different deviant behaviors, they might offer different detection opportunities. So to generate the exploit samples, we use Metasploit, which is a widely used penetration tool, testing tool in the industry. Since we want to label the measurements that are attributed to the various stages of the different stages of the malware execution, we instrument the boundaries of the stages with 1 byte debug trap instructions. And we also introduce variation. We use like different variation, different types within each stage across the samples. So next, in selecting the features that we want to use, we face several other challenges as well. We will briefly describe 2 techniques that we use to overcome the challenges. So the first challenge that we face is a classic signal-to-noise kind of problem. So it turns out that the perturbations that were caused by the malware execution are extremely small. Here, we plot the box plot of the measurements from the clean run and the different malware stages for a visual indication of the distribution and the deviation. So as we can see from the box plot, the deviations are not directly observable as the values are mostly clustered near 0. So to overcome this challenge, we use a popular statistical tool called the power transform, or also known as the Box-Cox transformation. So the power transform is a rank-preserving transformation that is commonly applied to data to make the data more normal-like. So for each event, we find the appropriate power parameter lambda such that the normalized median for the clean data is within an epsilon tolerance value of 0.5. And when used in our context here, the power transform positively scales the measurements and magnify any perturbations that were caused by the malware. So here is a visual example of what happens when we apply the power transform. So we begin, after applying the power transform, we begin to better observe the perturbations that were caused by the different stages of the malware execution, as we can see in these 3 different events. Now, the second challenge we face is an inherent limitation of the hardware performance counters that we use. So on the Intel processor chips that we use, the counters are limited to monitoring only up to 4 events concurrently at any one time. However, there are more than 200 over possible events that can be monitored. So how do we select the events that we want to monitor? Ideally, we want to shortlist groups of 4 events each that can best distinguish the malware stages from the normal code execution. So our approach here is a 2-step process. First, we shortlist the 19 events based on past program characterization works and based on our informed understanding of the malware behavior. So as you can recall in the previous slides, there are some nuances with the differences between the architectural and microarchitectural events. Therefore, we categorize these events into 2 main groups. So here is a more concrete example. So the architectural events gives us an indication of the execution mix of the instructions in any running process. For example, the number of load store instructions or the number of arithmetic instructions for a given period of time. The microarchitectural events, like you said earlier, as we have mentioned earlier on, describes the interaction of the software with the microarchitectural components in the hardware. And as such, they are very dependent on the specific system makeup of the system. For example, they measure things like the number of mispredicted branches or the number of mispredicted return instructions when the software executes. So next, we rely on the Fisher score, which we term as the F score here, this is a widely used feature selection technique that can pick out events that can have a better ability to distinguish between 2 classes of measurements. So put simply, F-score quantifies the degree of separation between 2 classes of measurements. So in order for us to do that, we compute the F-scores for each event. Each event will have 3 F-scores associated with it, 1 for each malware stage. Next, we rank the F-scores by grouping them based on microarchitectural only events, the architectural events, and combining both of the groups together. So with that, we have 9 candidate event sets with 4 events each. And then we label these sets so that we can refer to them as we build the models. We label this set with a prefix A to represent the sets that contains the architectural events. And we use M for the microarchitectural one and AM for both of them. So for example, if you look at the second event set with the label set M2, based on the F-score ranking, this 4 microarchitectural only events, we have the best chance of distinguishing the stage 2 payload from the clean measurements. So with the features that we want to use selected for the models, next we talk about the feature extraction and the model building itself. So we experimented with 2 ways of feature extraction. For the first non-temporal version, we create each sample using measurements attributed to the execution of X instructions. And that would consist of, this will create 1 time epoch sample. Now, the second method is to possibly exploit any temporal relationships among these kind of samples. We create temporal samples by grouping the consecutive non-temporal samples together. As for the machine learning technique, we use the one-class support vector machine to build unsupervised model of the baseline microarchitectural and architectural profile of normal programs. Since this is one class, so we train with data only from the clean runs. And we use the RBF kernel, which is the radio basis function kernel, to project the data onto a nonlinear feature subspace to do the training. And finally, for the training, we use an off-the-shelf SVM library called the libsvm, developed by National Taiwan University. And we modify libsvm to produce a numerical decision function output instead of classification. So this allows us to tune the knob and to allow us to change the detection thresholds that we want according to our use. Then we evaluate the models using holdout measurements from the clean run and the exploit runs. There are 2 key metrics that we use here to do the evaluation. So one is the receiver operating characteristics, which we commonly call it the ROC curves. So basically what the ROC curves does is that as you vary the threshold, the ROC curves shows like a trade-off between how correct we are in identifying the malicious samples and how wrong we are in flagging the clean samples as malicious. And the second metric that we use is the area under the ROC curves, which we call it the OC scores. So this is basically just a quantitative measure of the area under that. And the higher the OC scores, the better it is. And this allows us to compare between different models. And finally, we use the models to detect the exploits. In this work, we did not look at the remediation actions after the malware samples are identified. Now, I want to briefly run through some of the key results that we have for our work. First, I want to highlight some of the key detection performance results regarding the different stages of the malware. So here, we see the OC scores of the various models that are plotted as bar plots. So on the y-axis, this shows the OC scores. The higher the OC scores, the better the detection performance for the specific model. So on the x-axis, we see 9 event sets that we had shortlisted earlier to build the models. And then we further group the models into 2 separate groups with the non-temporal events models on the left and the temporal ones on the right. So note for the temporal models, we have actually left out the OC scores for the ROB stage. So basically, the reason for that is that we measured the raw shellcode execution to take between 100 to 6,000 instructions to complete. But when we use a sampling granularity of 500 and 12,000 instructions and combine like multiple non-temporal samples together, the execution of the raw shellcode, it constitutes only a very small portion of this temporal sample. So as a result of that, the entire sample looks like a normal sample. So we conclude that at least for the temporal version, it is not effective in sussing out like the deviation caused by the raw shellcode. And also the different shades of the bar plots represent the detection performance of that model in detecting that specific stage of malware. So for example, on the left, the non-temporal model using the event set A0 performs best for the detection of stage 1 shellcode compared to the ROP or the stage 2 shellcode. So let's zoom into like 3 of the non-temporal models that use both the architectural and microarchitectural events. Here we see the corresponding ROC curves for each of the set. So this is where we can get kind of a rough idea, a better sense of the trade-offs between the false positive versus the true positive. So next we zoom into the ROC curves for the same AM event sets for the temporal models, and we can easily tell that for the temporal models, it seems to have a better detection performance. So I want to briefly just summarize some of the key observations from the results that we have here. So the model seems to performs best in the detection of the stage 1 shellcode. So it appears from, when we analyze this a little bit deeper, it appears that the stage 1 shellcodes has peculiar characteristics that are not common in the normal programs. For example, in order to be portable across the different versions of like the programs, they actually have to be crafted as a position-independent code, which we call PIC. And this includes some tricks that they will have to use in the shellcode, for example, having to resolve the function addresses dynamically through like function hashes. And there are some like shellcode tricks that are also not commonly found in the user program. So this results in the model being best able to detect the perturbations caused by the stage 1 shellcode. And also there were better detection performance with the temporal modeling approach. And this I covered a little bit earlier, where we talk about how the detection performance for the ROP shellcode is not very good using this technique because they only constitute a small portion of the samples that we have. Next, I want to highlight some key results pertaining to the use of architectural versus microarchitectural events. So the architectural-only events with the prefix A models, they perform better than the microarchitectural events. But combining the use of both the architectural and microarchitectural events in the models, this achieves a better detection performance. Now for some results on the sampling overhead versus the detection performance. While the performance counters incur near zero overhead in monitoring the events, a pure software-only implementation in this work still requires us to interrupt the programs periodically to sample the event. So on the left, we measure the execution slowdown using different sampling rates. Note that the sampling rates on the x-axis is in the log scale. And on the right, we measure the corresponding detection performance for each malware stage and the temporal versus the non-temporal models for different sampling rates. So the cost of grain sampling rate that we use, the lower sampling overheads that we have, and consequently there's actually lower detection performance because as you increase the number of instructions executed within the actual sample itself, it creates a lot of noise within the actual sample. But the big picture that we get from here is that the gains that we get from lowering the sampling overhead far outstrips the deterioration that we get from the detection performance. So we want to kind of like reach a sweet point, and we found out that the sweet point is the sampling rate of about 512,000 instructions for the sampling rate. So some of the future work that we are looking at, in general, combining like multiple sensors typically increase the cost in terms of the attack effort to the attacker linearly for the attackers. So we want to explore ways to combine sensors like this that uses lower level features and other sensors that use like higher level features, and do it in a manner that will result in a more than linear increase of attack efforts for the attacker. So ideally, we want to be able to quantify this degree, as which we term as multiplicative effects of combining these sensors together. And also because there's no need to bridge the semantic gap, we want to actually explore using out-of-VM deployment in the VMI-based kind of method. And also, there is scope for further hardware support because in this case, we repurpose the use of the hardware performance counters for security. We might be able to add like additional hardware support to include counters that can give more meaningful features. So to wrap up, this is the first anomaly-based malware detector or sensor using lower-level microarchitectural features from the performance counters to detect malware exploits. And we have seen that adding microarchitectural features to the architectural ones improves the detection of anomaly that were exhibited by the exploit shellcode execution. And we have more details in the paper that describes and analyze quantitative and qualitatively the impact and difficulty of evasion attacks. So much so that in order for an attacker to evade detection in a mimicry attack, for example, the exploit crafting becomes a delicate and very precise kind of balancing act for them. So with that, I end my talk, and I'll be glad to take questions. Thank you. Which one was that?
Just before future works.
Oh, just before future works. Okay.
Why did the blue curve go up?
Oh, why did
from 256 to 512?
Yeah, we haven't actually been able to pinpoint the exact reason, because within the sample itself, because one sample may consist of 512 instructions of execution. Yes. So because the ROP shellcode only constitutes a small portion of that, without further instrumenting the code, we are unable to find out the specific reason.
So that seems like an anomaly. Another question, you might have mentioned it, but maybe I missed it. What attacks did you try for your results? Where did you get your attack samples?
Oh, we generated the attack samples from using Metasploit. So we use, it's all memory corruption kind of attacks. When you
Specific for this high-performance computing platform?
No, it's not the high. So are you referring to which one is it?
The ones that you tried here.
Oh, they are basically targeted on user programs that is running on the Intel processor chips. For example, like Internet Explorer, PDF Reader, and the Flash plugin that runs within the Internet Explorer.
Thank you.
Yep.
You probably have some backup slides about the evasion techniques.
Yes, I do.
Could you show them, please?
Fantastic.
I'd be interested.
Okay, so just very briefly, all right. So this is just some of the attacks that we have generalized for the mimicry evasion attacks. We only go into more details for the attack one padding, which is, the general thing is if an attacker knows, the assumption is that the attacker knows the way we are modeling the thing, and he needs to know exactly the events that we are using to model the thing. So with that in mind, what he could do is he could run the same thing on probably the same or similar system and find out what a normal model would look like and try to massage his attack code to reflect the same kind of normal code behavior in terms of the features that we are doing. So for example, for a padding attack, is if you have noticed that one of the features is very low in counts in his attack code, he might want to artificially increase that in his attack code. So using a padding attack, what he will do is he will include instruction segments that will artificially increase his event scores, and yet doesn't actually has no op effect because he still wants his attack to succeed, right? So he will have to include all this using that. And so these are some of the details that we have. So this shows like some of the anomaly scores. One of the more interesting things is that generally, as you increase like the paddings that he includes in the shellcode, the detection performance deteriorates a little bit up to a point where adding more padding will actually increase the anomalous working behavior of the attack code, as you can see from the mispredicted events here.
So I guess the biggest problem for the attacker is you can do this, but it's not portable. So this is, I guess, for an attacker's problem. You can actually do it on an individual case. But I think the cool thing is that it becomes very hard to port this to another machine, another installation.
Exactly, because he has to take into account not just the version of the programs that it's attacking, he has to account for the diversity of the systems that he wants to attack. Absolutely.
So I'm sorry if this is a very naive question, but so you said you can only capture 4 events at a time, right? Yeah. Or measure. So how difficult is it, or how frequently can you actually change those events you're looking at to make the evasion even more complicated?
So your question is how...
Could you measure for a certain amount of time and then switch to others and hopefully as rapidly as possible, so that then it makes the life of the bad guy? It's like doing a sampling, if you want, on the numbers.
This is one of the few defense strategies that we can use to change and minimize the kind of events that we use across time.
Okay, we actually don't have time for a question anymore, so please take that offline. Thank you very much, Adrian, for the very nice presentation.
Thank you.